In the more than 60 years where scientists have engaged in the search for extraterrestrial intelligence, SETI, several potential examples of technological activity, technosignatures and some sci-fi, have been considered. While most SETI surveys to date have focused on potential radio signals from distant sources, scientists have expanded the search to include other possible examples. This includes other forms of communication, directed energy, neutrinos, gravitational waves, etc., and examples of megastructures, Dyson Spheres, Clarke Bands, Niven Rings, etc. Examples of modern searches include Project Hephaestos, the first Swedish project dedicated to SETI, named in honor of the Greek god of blacksmiths. This project is focused on the search for technosignatures in general rather than looking for signals deliberately sent toward Earth. In a recent paper, a team led by the University of Manchester examined a Dyson Sphere candidate identified by Hephaestos. Their results confirmed that at least some of these radio sources are contaminated by a background active galactic nucleus. The team was led by Tong Tianwen, a PhD student in astrophysics from the Jodrell Bank Center for Astrophysics at the University of Manchester. The paper that describes their findings recently appeared in the monthly notices of the Royal Astronomical Society. Dyson spheres are a class of megastructures originally proposed by physicist Freeman Dyson, who proposed how advanced civilizations could create structures large enough to enclose their stars, thus harnessing all of their energy. Project Hephaestos, led by Professor Eric Zackerson, has published numerous papers exploring possible Dyson sphere candidates using different methods and data sources. The fourth and most recent paper in the series focused on 7 potential candidates, designated A to G, around M-type stars from a sample of 5 million detected by the ESA's Gaia Observatory. Previously, Run and his team have investigated these candidates to identify possible natural explanations. As they explored in a previous paper, these include dust-rich debris disks that absorb light and re-emit it as infrared radiation. This will lead to an observed infrared excess, which Dyson proposed as a possible indication of his proposed megastructure. However, as they indicate in their most recent paper, the project's measurements do not appear to resemble typical debris disks. As Garrett explained, when I saw the original results from Project Hephaestos last year, I was skeptical. They had surveyed 5 million stars, and if you do that, there's a good chance your measurements might include emission from background sources. You don't expect stars to show radio emission at this level, and it basically tells you that the radio emission is probably coming from background radio galaxies. But then you also need a special kind of galaxy that is faint in the optical but very bright in the infrared. The only galaxies I knew that had this characteristic are D to O.GS, dust-obscured galaxies. The team was also inspired by another paper by Jason T. Wright, a professor of astronomy and astrophysics at Penn State, the director of the Penn State Extraterrestrial Intelligence Center, and a member of the Center for Exoplanets and Habitable Worlds. In this paper, Wright hypothesized that a true Dyson sphere might use radio emissions to discharge waste heat. This led them to consider the possibility that these candidates were indeed Dyson spheres. As Tong Tian explained, they were also inspired by previous research by Garrett. Mike briefly argued in 2015 that even in a Kardashev Type 1 civilization, where energy consumption is significantly higher than that of humans on Earth, their radio communication signals are too weak to detect. However, the Dyson spheres could correspond to a Kardashev Type 2 civilization, one that harnesses over 1 billion times more energy than a Type 1 civilization. Therefore, regardless of whether the beings reside on planets or elsewhere near the Dyson sphere, it might be possible to detect their use of similar electromagnetic technologies. To investigate these possibilities further, the team searched through data obtained by the Enhanced Multi-Element Radio Link Interferometer Network and the European BLEI network for data on the brightest radio source, Candidate G. To their surprise, They found that 3 candidates from Project Hephaestus had radio counterparts in the astronomy databases. As Tontian explained, the most logical explanation is that these signals, including candidate G, were due to contamination from bright radio sources, active galactic nuclei in the background. They shouldn't belong to one civilization. Otherwise, many anomalous stars would be connected as a swarm in the sky, not isolated 7. At that moment, we realized that either different extraterrestrial civilizations located hundreds of light years away all have mastered the same or similar advanced radio emission technologies, or these signals originate from some form of natural contamination. We prefer to assume that they were some natural objects beyond the Milky Way, and most likely to be hot dogs. These results effectively confirmed their earlier hypothesis that at least some of the candidates identified by Project Hephaestus are contaminated by bright radio sources that are also very bright in the infrared wavelength. This causes them to mimic the characteristics that Freeman Dyson predicted and what astronomers expect from Dyson Spheres. However, this does not rule out the remaining 6 candidates and highlights the importance of thoroughly analyzing each candidate with high-resolution radio observations. We don't know that all of the candidates are contaminated, but some, maybe all, probably are. I really hope some of them are indeed good Dyson Sphere candidates, said Garrett. This all shows that a multi-wavelength approach is really required when looking for candidates in order to rule out background contamination. The development of new astronomical instruments does not follow the rapid update cycles of consumer electronics. It takes decades, added Tontian. Gaia, launched in 2013 and recently decommissioned, and WISE, launched in 2009 and expired in 2024, provided a crucial observational window. The next generation of similar probes may not be available for a long time, making it unlikely that a large-scale Dyson Sphere search program, like Project Hephaestus, will be conducted again in the near future. So the current 7 Dyson Sphere candidates deserve to be carefully examined